Good morning. Today we're going to be covering translations. Our learning target today is I can translate figures using a translation vector. So we're going to be talking lots about vectors today, continuing what we finished off in our last video, and then working solely today on transformations. And this transformation today is on translations. So keep that in mind. This will be strictly on translations today. So getting started, we're going to go ahead and recap what the definition of a vector is. Again, this is an extremely important definition for both physics and high-level calculus. So knowing what a vector is will be extremely helpful down the road for you guys if you choose to do anything with physics, or if you choose to go into a math direction and take these high-level calculus courses, often found in Calc 3 and such. So a vector is just a quantity that has both direction, and that's cardinal direction, meaning north, south, east, or west. I can say like north, east, or south, southwest. Those are different cardinal directions that we can use. And then they'll also have a magnitude, so they'll have a speed as well. Now we have some important terminology down here, some important definitions. Our first definition is initial point. The initial point on a vector is the starting endpoint. So we see that vectors and rays look very, very common. They both have a starting point. We can call that the initial point. And then they both have an arrow going in one direction specifically. Now, with a vector, at the tip of that arrow, we call that the terminal point. That's our ending point. That's where we're trying to get to. Our initial point is, of course, our common endpoint where we begin, and that will always be our starting point, our initial point. And then along with naming vectors, even those are slightly different than naming rays, because oftentimes rays and vectors look indistinguishable besides seeing the terminal point or in which the way that they are written. As we can see, we have ray EF up here, and we know it's a ray because it has an arrow in one direction. And then we also have vector V. So the main difference here is that V has half an arrow showing that's a vector. So that is the main difference, and you'll only know the difference by the name itself or if they tell you that we're doing a transformation. So if you see a translation occurring, you can automatically assume that's a vector rather than a ray. So translations can be represented using vectors. For instance, we have this component form right here, 3, 5, and again, those have those fancy brackets on either end, the pointy brackets. That's how we know that it is a component form vector. So what this is telling me is that I need to move my x value 3 units, and since it's positive, it's going to go right. If it was negative, it would go left. Then the 5 is in the y place, so that's telling me that my y value will go up 5 units. If it was negative, it would go down 5 units. So depending on whether it's positive or negative tells us the direction in which we're going. So this is telling us to move 3 units right and then 5 units up. So if I take my initial pre-image, triangle ABC, and I were to translate it along that vector, 3, 5, I'd move each of my vertices 3 units right and then 5 units up. I don't need to focus on any of the points in between, because if I do that with each of my vertices, then I can draw the lines in between my vertices, creating all those points in between. So as long as you focus on just the vertices that you move, then you can draw everything else in between afterwards, and it'll work perfectly fine. Now, if we're looking at this, we can see that we have this red vector here, and that vector is actually the vector 3, 5, the one that we're traveling along. So we can see that each of these points moved along that vector to give us our new image. And that's all you have to do when you're translating. Take each point, take each vertice, and move it along your vector. So, a vector can also be named using component form, and again, component form has the pointy brackets, and it's written as A, B, where A is your x value of movement, B is your y value movement. That specifies the horizontal change, again, that's x value movement, as A. In the vertical change, again, that's our y value movement, as B. And that's going from the initial point to the terminal point. So I'm always starting at my initial point. So initial point always is the end point, terminal point always has the arrow at the end of it. So if I were to name this vector here in component form, it'd be vector 5, because again I see this 5 down here, that's telling me that I'm moving 5 units over, and then I'm going up 1, 2, 3, so it'd be 5, 3. You can tell by the translation vector that each point will be translated 5 units left and 2 units down. And again, we can see that because we have this vector here. I can just count 1, 2, 3, 4, 5. That's 5 units left. And then 1, 2, that's 2 units down. So you can just count. That's okay. That's what I expect you guys to do as you go through these. So this vector can be represented as -5, -2. So it can be represented by this component form here. We should be able to look at both an image and a pre-image. So if I have this pre-image here and I have the image going along with it right here, I should be able to look at these and determine exactly what the value of the component form vector is. So I would just count from A to A prime. Now if I count from A to B prime, that's going to be wrong. I must match these up with each other. So A goes with A prime, B goes with B prime, C goes with C prime, F goes with F prime, E goes with E prime. So they all must match up. We must match these together before we do anything with them. So if I'm going from A to A prime, I can count 1, 2, 3, 4, 5, and then I'd go down 1, 2. Since their orientation is the same, meaning they're facing the same way, I know that it's just a translation that's occurring. It's not a rotation or a reflection or anything like that. Since they're facing the same way, it's telling me it must be a translation. So therefore, I can just say, okay, well, this is a translation of -5, -2. And that's how you can get that vector as well. That works perfectly fine. All right. So suppose the coordinates of triangle ABC are right here. A is at -1, 3, B is at -2, 1, and C is at -4, 4. Is translated along the vector 5, -5. Predict which quadrant the new image will be in. Explain how you know. So again, I drew up the quadrants in the corners here. So 1, 2, 3, and 4. If I were to move this 5, -5, so I move each of my vertices 5 and then -5. Well, predict which quadrant the new image will be in. Well, I'm going to predict that's going to be in quadrant 4. And the reason I predict that is because each of my points will be in quadrant 4 if they travel along that vector. So if all 3 points are in quadrant 4, then I can assume that all those points in between will also be in quadrant 4. So all the points move there. All right. Which translation vector will map triangle ABC to triangle A prime, B prime, C prime? Again, to do this, take from your pre-image a point and correspond that to the corresponding point in your image. So C and C prime as an example. I could have done A and A prime or B and B prime. From there, I'm going to draw my vector from my initial point, C, to my terminal point, C prime. Now I'm just going to count. Well, to get from C to C prime, I need to go right. 1, 2, 3, 4. So that's a +4. And I need to go down. 1, 2. So that's a -2. So therefore, my component form vector will be the vector for -2. Now I could have done that from point A as we see right here, same exact thing. I could have done it from point B. We got the same exact thing. So again, we're just counting along our grid here. And again, I could have done from B to B prime, C to C prime. All right. A translation along the vector -4, 5 maps point P to point Q. The coordinates of Q are at 6, -3, so I know where we're going to end up. This is our image. We need to find our pre-image still. So to find our pre-image, to get to our image, we went along this vector -4, 5. To get to my image, I'm going to do the opposite of that. So I'm going to go to the right 4 and then go down 5. That'll lead me to point P, which is down here at 10, -8. Now if I go from point P to point Q following my vector, that's -4, so 1, 2, 3, 4, and then up 5, 1, 2, 3, 4, 5. That maps me at point Q, so point P is in the correct spot if I followed along this vector once again. So if I need to find my pre-image, I need to do the opposite vector. So I need to go the opposite direction. So if it was -4, 5, I travel along 4, -5. We're just going in a backwards process here. All right. Now, For this one, draw the image when figure ABCD is translated along vector -5, 4. So, when I see something like this, I only need to take one point and have it travel along that vector. For instance, if I take point A, I have it travel along the vector -5, +4, I'll end up here in quadrant 1 for point A. Or sorry, point A prime. Now, I know that D is 2 units below A. So D prime should be 2 units below A prime. Similarly, B is 4 units to the right of A. So B prime should be 4 units to the right of A prime. So again, I don't need to do this with each point and travel along the vector. You can, but all I really need is one point, and then using the orientation and what we know from our pre-image to construct the rest of our image. Now, of course, if you're like, I like doing vectors and I'll just travel along the vector anyway, then you can definitely do that for each point. It's no issue at all. But just know that if I take one point, well, the rest of the points should be in the same positions corresponding to that single point. All right, our final question for the day. This one is important, so take note of it. So for this one, a translation vector maps points in quadrant 3 along vector xy to points in quadrant 1. What can you conclude about the variables x and y? So I know that we're starting in quadrant 3 over here, and we're moving to quadrant 1 somewhere over here. Now, if I'm traveling along this vector, I know that x is going to the right because I must move to quadrant 1, which is to the right of quadrant 3. So my x values are going to the right, which means that x is positive. X must be positive because I'm going in this direction. As for my y's, well, I'm going to quadrant 1, so my y's need to go up in value, so they also must be positive. If they're negative, then I'm going downward to quadrant 4, right? I'm staying in quadrant 4. But if they're positive, then I would be going upward towards quadrant 1. So therefore, x and y must both be positive to make a point from quadrant 3 to move to quadrant 1. Because again, x is going in a positive direction here, and we can see y going in a positive direction, which means that they must both be positive in order for us to move to that specific quadrant. Alright, that is it for today's video. If you guys have any questions, please leave it in the comments. Other than that, thank you guys for watching. I'll talk to you soon. Take care.